Welcome to Mrs. E's Chemistry. In this video, we'll learn about the forces that keep molecules together in a liquid or a solid. So far in this chapter, we've been talking about gases and how the molecules in the gas phase are so far apart that the interactions between them are insignificant. In other words, the attractions and repulsions between molecules in a gas are negligible. In a solid or liquid state, the molecules are very close together and they interact with each other with a sizable amount of strength. These attractions and/or repulsions between molecules play a large part in determining different physical properties of substances. We call these forces intermolecular forces, or IMF for short. Inter means between the molecules, and the prefix intra means within the molecules. In the past, we've discussed covalent bonds, which are the bonds or forces that hold atoms together within the molecule. Intermolecular forces is what we are going to talk about now, which are the forces that hold the molecules together between the molecules. Intermolecular forces, or IMFs, are much weaker than covalent bonds. The IMFs in a solid need to weaken in order for the solid to melt into a liquid, and the IMFs in a liquid need to completely break or sever in order for the liquid to boil and become a gas. In these phase transitions, only intermolecular forces, or IMFs, are broken and formed. The covalent bonds within each molecule always stays intact. We've seen this picture before when discussing different phases. As we move from right to left, the substance is a gas, then liquid, then a solid, and the intermolecular force strength is increasing. As we move from left to right on this picture, from solid to liquid to gas, the kinetic energy, or temperature in Kelvin, increases. Imagine taking a cold drink outside on a hot day. Soon, your glass may begin to sweat on the outside. That is water vapor that was in the air, condensing or becoming a liquid as it comes in contact with your cold drink. The kinetic energy of the gas, or water vapor, decreases as it gets colder and the molecules move closer together, and they start forming intermolecular forces between each other and turn into liquid drops on your glass. Butane is a gaseous phase in the gaseous phase at room temperature. But if you apply enough pressure, it will turn into a liquid. That is why you hear liquid sloshing around if you shake a lighter. It's been pressurized inside the lighter. When you let some out, it immediately turns back into a gas since it's now under normal pressure conditions. It combusts because of a spark that is made when you click the lighter on. Continuing on this topic of pressure versus volume, think about what happens when you increase the pressure of a gas at constant temperature. The volume decreases. If you apply enough pressure, the volume will decrease so small that the molecules are very close together, close enough that they begin to interact with each other and the intermolecular forces between them form. This is when the gas turns into a liquid, even though the temperature never changed. All right, now let's learn about these intermolecular forces, or IMFs, and how they work. They are also called van der Waals forces, after a scientist who is famous for his pioneering work on liquids and solids. These are the three different types we're going to learn about in this chapter, and today we're going to learn about the first two listed here, London dispersion forces, also abbreviated LDF, and also dipole-dipole interactions. All molecules experience London dispersion forces. Nonpolar molecules only experience London dispersion forces. In nonpolar molecules, the electrons are evenly shared throughout the whole molecule because the molecule is symmetrical. Therefore, nonpolar molecules don't have permanent dipoles. However, because the electrons are constantly moving around at any given instant, the electrons may be unevenly distributed throughout the molecule, giving the molecule a temporary dipole. These egg-like pictures are representing a whole molecule, with the blue side representing a higher electron density, meaning more electrons are around the blue side of the molecule, giving that side a partial negative charge. And the opposite side, the side shaded red, is the partial positive charge. This temporary partial negative and partial positive attracts neighboring molecules that also have temporary partial charges, and this is the force that holds these molecules together in the liquid or solid phase. London dispersion forces are what we call these, and they are present in all molecules, polar and nonpolar molecules. However, these nonpolar molecules only experience this type of intermolecular force, the London dispersion force. Polarizability is the tendency of the electron cloud to distort, with more electrons on one side than the other. The more electrons a molecule has, the more polarizable it is, and the stronger the force that holds the molecules together, and therefore the more energy required to break the intermolecular forces and turn the substance into the gas phase. The shape of the molecule will also affect how strong the London dispersion forces are. If the molecule is shaped long and skinny, there is more surface area and more contact between them and the neighboring molecules. This makes the LDFs, or London dispersion forces, stronger and causes this molecule to have a higher boiling point because it requires more energy to break the intermolecular forces. Larger surface area causes stronger forces holding the molecules together in a liquid. This will in turn require more energy to break these forces and turn the substance into the gas phase. We can see from this slide that each of the different molecules have the same number and type of atoms. However, they are all shaped differently. N-pentane, on the far right, has the longest shape, causing it to have a larger contact area with the neighboring molecules, which gives it the highest boiling point of all three of these substances. The larger the molecule, the more electrons the molecule has, which means it is more polarizable. This causes the stronger LDFs, or London dispersion forces, which require more energy to break, which translates to a higher boiling point for the molecule. To demonstrate this concept, let's think about the compounds from group 14, or group 4A, bonded to hydrogen. Here's the Lewis structures for each of the compounds. The only thing different is the center atom. As we move down the column on the periodic table, or across this slide from left to right, the atom in the center becomes successively larger, which means they have successively more electrons than the one before it. Since we know that the molecule with more electrons is more polarizable, which leads to stronger London dispersion forces in the molecule with the most electrons should have the highest boiling point. Looking at this graph, the boiling point temperature increases as we move up the y-axis from negative 200 degrees Celsius all the way up to negative 40 degrees Celsius. Across the x-axis, the period that the center atom is from, the period on the periodic table, increases. Period 2 is where we get carbon from, period 3 is where we get silicon from, and so forth. Sure enough, CH4, having the fewest electrons, has the lowest boiling point. And SNH4, with the largest number of electrons, has the highest boiling point of these four molecules. So far, we've looked at London dispersion forces that all molecules experience, but nonpolar molecules only get to experience this type. And now we'll look at dipole-dipole interactions. Polar molecules have permanent dipoles because their electrons are not evenly distributed throughout the whole molecule. These molecules always have one side that is partially negative and the other side partially positive. The partial negative side of one molecule attracts the partial positive side of the neighboring molecule. And these IMFs are what we call dipole-dipole interactions or attractions. The more polar the molecule, the stronger the dipole-dipole interaction, and the more energy will be required to break these forces and turn the substance into the gas phase. In short, the more polar the molecule, the higher the boiling point that molecule has. When we are comparing molecules that have similar molecular weights and therefore a similar number of electrons, dipole-dipole interactions are stronger than LDFs, or London dispersion forces. Let's look at some comparisons here between HCl and F2. HCl is a polar molecule. Therefore, it experiences dipole-dipole interactions, which are stronger intermolecular forces. Its boiling point is 188 Kelvin, compared to the boiling point of F2, which is only 85 Kelvin. F2 is nonpolar and only experiences London dispersion forces, which are weaker forces holding the molecules together in a liquid. Predict which will have the higher boiling point between N2 and CO, and explain your reasoning. CO is a polar molecule. Therefore, it experiences dipole-dipole interactions, which is a stronger force than London dispersion forces when we're comparing molecules with similar molecular weights and similar number of electrons. Therefore, carbon monoxide will have the higher boiling point because it requires more energy to break apart these stronger intermolecular forces. Predict which will have the higher boiling point between ICl and Br2, and explain your reasoning. ICl is polar, therefore it has stronger intermolecular forces, the dipole-dipole interactions, and therefore it's going to have the higher boiling point because it will require more energy to break the intermolecular forces in ICl than in Br2, which is nonpolar and only experiences London dispersion forces. These are sample test questions. Pause to write out your answers and an explanation. These are the answers. Notice you can't just say that one molecule is bigger and then call it good. You have to explain why being bigger gives it the higher melting point or boiling point. And that's because the molecule with more electrons is more polarizable and therefore has the stronger intermolecular forces, which leads to a higher melting point or boiling point. So in summary, these are the 3 intermolecular forces that we're going to learn about in this chapter. In this video, we learned about London dispersion forces and dipole-dipole interactions. And in the next video, we will learn about hydrogen bonding.